In this video, we will try to describe the idea of fugacity, why it's important, where it comes from, why we're interested in using it. And we'll start out by looking at two phases, an alpha phase and a beta phase. We won't specify any more about the phases right now. But what we're showing is the concentration of component A in each of the phases. And initially, these phases are not in equilibrium. And the question is, which direction does component A move? What's direction of mass transfer to get to equilibrium? We're always looking at how systems approach equilibrium. And in this case, we might look and say, well, a very high concentration of A in this phase, we might expect mass transfer to go to the lower concentration. However, for this particular system, if this phase was water vapor, and this phase was liquid water, and we were at 45 degrees C, then mass transfer would be in this direction, because this concentration, if we look at steam tables, is actually higher than saturation pressure. So equilibrium would be a decrease to saturation pressure. And so this means we can't use concentration as our determination of direction of mass transfer. Certainly concentration matters and that it affects fugacity, but we're going to use fugacity or chemical potential as our determining factor. If the chemical potential is higher in the alpha phase than the beta phase, so chemical potential in the alpha is higher than the beta, and therefore mass transfer goes from alpha to beta. And another way of looking at this, it means the fugacity of water is higher in the alpha phase than the beta phase. So the chemical potential is related to the Gibbs free energy, and we use Gibbs free energy. We look at this a couple of ways, but the Gibbs energy in the vapor phase would be the enthalpy per mole or per kilogram. Vapor phase minus the temperature times the entropy in the vapor phase. And at equilibrium, that enthalpy in the liquid phase minus Ts, so G in the vapor phase, G in the liquid phase, those are equal at equilibrium. That turns out to be our criteria for equilibrium. If we rearrange this equation, we know it's H vapor minus H liquid over temperature is vapor minus S liquid, which means delta H of vaporization over temperature is equal to delta S of vaporization. Heat of vaporization divided by temperature is the entropy change of vaporization. This is how we originally derived entropy, where entropy change we defined as dq reversible over T, and for phase change, T is constant, Q is delta H when we carry out vaporization at constant pressure. And so this equation follows from our definition of entropy, shows that the Gibbs free energy is the same in both phases. So let's look at how we get fugacity from Gibbs free energy. And we'll go back to the first law, closed reversible system, change in internal energy, differential change is the heat added and the work added. If it's reversible, then we can write dq in terms of entropy change. And again, if it's reversible, we can write work as minus PdV. Now, delta H is defined as delta U plus delta PV, or DH is DU plus DPV. So we can make the substitution from DU. These two terms cancel. And DH is TDS plus VD. And now one more step, DG, DH. So we're making the same type, again, substitution, DH, TDS plus VDP minus TDS minus SDT. So the differential change in Gibbs free energy, and again, you notice this term cancels, VDP minus SDT. And so what we're going to look at, a lot of our calculations, is what happens if we change at constant temperature. Then dP is VDP. So we can calculate the change in Gibbs free energy from volume and pressure changes at constant temperature. And look at, for example, an ideal mass, what the change is going to look like then dG for an ideal gas is RT over P dP. Well, remember, the volume I'm using here is the specific volume, the volume per mole. So RT dP over P. And so this means change in Gibbs free energy for an ideal gas is RT d log of P. And so what's been done then for real gas is say, we like this form, so we're going to introduce a new variable called the fugacity. It's the value we put in here to make the Gibbs free energy change correct for gas. So if we were to subtract these two equations, the real and the ideal, and just divide by RT to make dimensionless, on the right side we'd have d log fugacity over pressure, and this is the fugacity coefficient, a dimensionless variable. So if we were to go back and remember that our constant temperature dG is VdP, we could subtract that equation for real gas, so got this real ideal gas, and we could write this in terms of a compressibility factor Z, and compressibility factor is 1 for an ideal gas, dP, so Z minus 1, or P over P, tells us this change in difference between ideal gas and real gas. Note that as pressure approaches 0, then G approaches the ideal gas value. So the real gas value and the ideal gas value Gibbs free energy are the same at low pressures where gases become ideal gases. So this means an ideal gas, the fugacity is just the pressure. For real gas, we have to use information like the equation of state, integrate this, determine the fugacity, because we have changing Gibbs free energy in terms of Z. We also have it in terms of fugacity pressure. And so if we combine these equations and won't go through the details, then fugacity given pressure for an ideal gas is equal to this integral, 0 to the pressure we're interested in, compressibility factor minus 1 P over P. So we use the equation of state, we can do this integration and determine fugacity for a real gas, any pressure. Ideal gas, we know the fugacity. So the question is, for a liquid, what is the fugacity? So the thing that is critical is to keep in mind what we showed way back here. Gibbs free energy in liquid and the vapor are the same at equilibrium. So we're looking at a one-component system. If the Gibbs free energy in a liquid equals the Gibbs free energy in a vapor, that means from our definitions, the fugacity in a liquid is fugacity in a vapor. And so at vapor-liquid equilibrium, we have both phases present. The fugacity in the vapor is going to be the saturation pressure if it's an ideal gas. That means the fugacity in liquid is the saturation pressure if indeed the saturation pressure is low enough that we can assume ideal gas. So now we have fugacity in a vapor for an ideal gas. We have a way of calculating fugacity for a gas that's not ideal if we have more information about how non-ideal it is. And then for liquid, saturation conditions to fugacity is the pressure. For a liquid at higher pressure, so liquid where the pressure is greater than saturation pressure, first thing to realize is not much changes. So these ranges increase the pressure, enthalpy, internal energy, entropy, etc. don't change. And since G is H minus Ts, if enthalpy and entropy don't change much, it means the Gibbs free energy doesn't change very much. And so indeed is a small change. And this small change, in the interest of time here, the fugacity would be fugacity at saturation pressure, which is going to be very close to saturation pressure. And then just from that definition, we have this exponential. This term is close to 1, and so it takes high pressures to change the fugacity very much for the liquid phase.
okay. Okay, so does that help? Somebody has to answer. हेल्प हुआ उससे वीडियो से? Nobody understood what was that video?
नहीं सर, इतना समझ नहीं आया।
नहीं सर,
इतना समझ में नहीं आया। ओके, सबका सेम प्रॉब्लम है, ठीक है?
Yes,
तो
sir.
मेन थिंग आई थिंक वी शुड थिंक अबाउट, स्टार्टिंग में क्या बताया उसने? He gave an example of two phases in equilibrium, right? Concentration was more in the liquid phase, concentration was less in the vapor phase. So individually we felt that okay, the mass transfer should take place from liquid phase to vapor phase, बराबर? Alpha and beta phase, बराबर? But that was not the case because vapor phase में saturation ज़्यादा था, concentration at that temperature. So that is why the mass transfer was taking in the reverse direction. So just looking at the concentration, we cannot say in which direction the mass transfer will take place. We have defined different terms like chemical potential, and that is what is important for mass transfer. Right? So just like if you see, let me share this one. Can you see this white screen?
Yes sir.
Sir,
Right? So you are able to see this because last time I showed Microsoft whiteboard, you are not able to see. That's why I'm asking you. So let's see. If I take temperature, what does it? Temperature shows what? What is it used for? Temperature used for what? हीट ट्रांसफर में क्या यूज करते हैं टेम्परेचर हम? What is the temperature indicator of what?
The hotness of
Degree of hotness.
degree of hotness of the body.
Degree of hotness. स्टार्टिंग में क्या बोला था मैंने? When we started fugacity, temperature is a what do you call? Used for thermal heat.
Measure of how fast molecules are.
So if you really see, Q is equal to some function of temperature, right? ठीक है? हीट ट्रांसफर पढ़ा है ना आपने? So temperature is a driving force for heat transfer. If temperature difference is not there, then there is no heat transfer. बराबर है? Similarly, if you have volumetric flow rate, it's a function of pressure or pressure drop. बराबर है? आवाज नहीं
Yes,
आ रहा
sir.
होगा. Okay, so what you see here is the temperature is the cause and this is the effect. If there is no temperature driving force, there is no heat transfer. So cause is the reason why heat transfer takes place is because there is a temperature difference. Similarly, reason why liquid flows or gas flows or vapor flows is because there is a driving force in terms of pressure drop or pressure difference gradient. Right? Similarly, if you want to talk about mass transfer, now we need to define some gradient, right? Some cause, and that we define as chemical potential. Not concentration. This may mu may be having some relationship with concentration, but actually the driving force for mass transfer is chemical potential. And chemical potential we have seen is related to pressure for ideal gas and we have defined as fugacity for real gas. तो यार अल्टीमेटली यू वांट टू सी कि मास ट्रांसफर जो हो रहा है या रिएक्शन जो हो रहा है वो कैसा हो रहा है. So if you want to define this m term mass transfer, you need to have some way to define this gradient or driving force for mass transfer or reaction, and that is what we are doing right now. We are defined chemical potential, which is partial molar Gibbs free energy, because Gibbs free energy is the net work available in any system, right? मास ट्रांसफर के लिए भी वर्क करना पड़ेगा, सो वर्क अवेलेबल है तो मास ट्रांसफर होगा. रिएक्शन के लिए भी सम वर्क हैज टू बी डन. कुछ there's nothing without input, right? Input has to be some work, some energy, and the Gibbs energy is that energy which is driving mass transfer, phase equilibria, chemical equilibria. And that is why we are saying that okay, we need to define something. We cannot use concentration. Concentration is not the driving force for mass transfer. We have defined another term which is really the driving force, which is chemical potential, partial molar Gibbs energy. That is what is the indicator of energy for fluid flow, fluid phase equilibria, and chemical equilibria. ठीक है, समझ में आया क्यों डिफाइन कर रहे हैं हम ये सब chemical potential, and then finding a relation of chemical potential to fugacity, because chemical potential for ideal gas we have seen it is RT ln P, pressure. So for ideal gas we can definitely find chemical potential from pressure, but for real gases we cannot find that. So what we see here, we have done this yesterday. So what we saw is dg is equal to RT dln. So if you know ideal gases के लिए, you can find change in Gibbs free energy based on pressure, because we need to see measurable quantities. Chemical potential cannot be measured, so we have to have measurable quantity like pressure, temperature, volume, which can be easily measured, which can be used to define these terms, which are indicators of equilibrium. Why we are defining this? Ideal gas के लिए pressure can be used as a means to calculate Gibbs free energy change. So that's similarly we define for real gas, because real gas pressure is not important. What is important is we are defining as fugacity, pressure for ideal gas. समझ में आया? Is it okay? Is it clear? Yes, no, don't know. Answer has to be there. Silence is not an answer.
Yes, तो थोड़ा बहुत समझ में आया. Yes, sir.
Who's that? दीक्षिता समझ में आया?
Yes, sir.
देवेंद्र?
Yes, sir. समझा.
मुर्तजा? मुर्तजा? शिवानी?
हाँ सर समझा.
So just like we define temperature as a driving force for heat transfer and pressure as a driving force for fluid flow, similarly we have defined a driving force for mass transfer and chemical reaction, and that driving force is chemical potential. But because it is not measurable, we cannot measure it, so we have to define it in terms of something else. So we start with ideal gas, which is easy to use. You know everything about ideal gases. So from ideal gas, we derive an equation for change in Gibbs free energy, because we know that once you know Gibbs free energy, we can find out chemical potential, because dG and mu are related, right? So we are going indirectly from pressure to dG, and then we get chemical potential. For ideal gas, it is easy because we have a relationship. We can use this thermo equation, dG is equal to VdP minus SdT, and we get this equation. But for real gases, we cannot use pressure because pressure is not a correct indicator of driving force. So we define another term which is called effective pressure, and that is called fugacity. Okay. So now, if you want to find out change in Gibbs free energy from state 1 to state 2, which is related to fugacity 1 and fugacity 2, what we'll get is G2 minus G1 is delta G, or change in Gibbs free energy, is equal to RT ln F2 by F1, right? So if you know how to define F1, fugacity in one state, you can find fugacity in second state, because we can measure free energy change going from state 1 to state 2. So fugacity in any state can be evaluated if the fugacity is assigned a specific value in a particular reference as standard state. As I said, जैसे temperature में we have defined 0 degrees and 100 degrees, right? They are essentially arbitrarily defined. So we define, when I say 0 degrees as a melting point of ice, then I can say relative to ice, how hot is the temperature? How much more is the temperature? Okay, so when I say 5 degrees, थोड़ा ज़्यादा है. So it's relative. So everything is relative because there is no absolute thing. There is no absolute temperature. वो बाद में define किया, but first we define centigrade, right? So we defined, or we divided the scale between boiling point and freezing point into 100 equal divisions, and that tells us how the temperature varying. Is it close to boiling point? Is it close to freezing point? Is it in between there? How much is the temperature? Similarly, if we define for fugacity some standard state or F1, then we can find out how much is F2. Okay, so if you look at ideal gas, delta G is RT ln P2 by P1. So this equation is applicable for ideal gases, and this equation 3, is applicable for real gases as well as ideal gases. Real gas is ideal gas at low pressure. Right? So when I say this equation is applicable for real gases, that means it can be applied for ideal gases also, because any real gas reduces to ideal gas at low pressure. Right? So if you compare equation 3 and 4, what you get is for ideal gases, F2 by F1 is equal to P2 by P1. Right? That means fugacity is proportional to pressure, directly proportional to pressure. So now we have a way to find out fugacity for any gas, right? So if you can measure the pressure, then we can find out the fugacity of any gas at any pressure. And that's how we go about it. So this is the relation, F is equal to K into P. And for ideal gas, K is equal to 1. That means fugacity is equal to pressure. And that is how we define a standard state. That means if you say the pressure is very low or gas is behaving like an ideal gas, then the fugacity of that gas at that pressure is equal to pressure. Understood?
सर वो F
Yes,
is equal to P
sir.
कैसे आया?
हाँ?
हेलो,
Yeah.
F is equal to P कैसे आया वो नहीं समझा, मतलब K1 कब होता है?
ये F2 by F1 equal to P2 by P1 है.
हाँ सर.
ये दो इक्वेशन कंपेयर किया हमने. Equation 3 is delta G is equal to RT ln F2 by F1. This is for real gases, right? And for ideal gases, delta G is equal to RT ln P2 by P1. Now, if you apply both these equations to ideal gas, because real gas is also ideal at low pressure, right? तो दोनों इक्वेशन अगर हमने आइडियल गैस को अप्लाई किए तो लेफ्ट हैंड साइड सेम है, RT कैंसिल हो जाएगा, तो ln F2 by F1 equal to ln P2 by P1. That means F2 by F1 is equal to P2 by P1 for ideal gas, right? So F2 is equal to P2 and F2 is some constant due to P2, right? You can say F2 by F1 is equal to P2 by F1. That means fugacity or F is proportional to pressure. जैसे हम लिखते हैं ना V2 by V1 is equal to what? आइडियल गैस के लिए PV equal to RT लिया, right? If you keep pressure constant, what happens? How is volume related to temperature?
V1 by V2 is equal to T1 by T2.
Yes. Similarly, F2 by F1 is equal to P2 by P1, right? So उसमें क्या है? Volume is proportional to temperature, right? For ideal gas at constant pressure. यहाँ पर fugacity is proportional to pressure. राइट? प्रेशर बढ़ेगा तो fugacity बढ़ेगा, प्रेशर कम होगा तो fugacity कम होगा. अंडरस्टूड?
हाँ सर, वो स्टेट नहीं समझा मुझे कि K is equal to 1 वो कब होता है? F is equal to
हम
P for
define
ideal
कर रहे हैं because we know for ideal gas this is the equation, right? आइडियल गैस के लिए इक्वेशन हमने डिराइव किया है, डेल्टा जी को RT ln P2 by P1.
हाँ.
राइट? ये डिराइव किया हमने, राइट? नाउ इफ यू पुट F P is equal to F by K, यहाँ पर प्रेशर के ऊपर F by K डाला तो क्या हो जाएगा? F2 by K divided by F1 by K, बराबर? K कैंसिल हो जाएगा, गेट F2 by F1. ये इक्वल टू कब हो जाएगा? when will this equation become equal to 1? इक्वेशन 3 इक्वल टू इक्वेशन 4 कब होगा? इक्वेशन 3 में क्या है? RT ln F2 by F1, right? Now this equation is applicable for ideal gas as well as real gas, right? दोनों के लिए applicable है. And this equation is applicable only for ideal gas. So if you take ideal gas, equation 3 and 4 has to be equal for ideal gas. Correct?
Yes sir.
Right? And when will that be? When will equation 3 be equal to equation 4 for ideal gas? When F is equal to P. Remember? When F2 is equal to P2 and F1 is equal to P1, then only this equation is equal to equation 4.
Yes sir, got it.
Right? So that means in that case we say that for ideal gas K is equal to 1 and therefore F is equal to P for ideal gas. This is the only condition under which those two equations will be equal for ideal gas. Okay? And for real gas, F is not equal to Kp. We cannot take K equal to 1 for real gas. It is only for ideal gas, K is equal to 1. Right? Or we can say that F by P is not equal to constant for real gas. But for ideal gas, it is equal to constant, which is 1. So as the pressure is reduced, the behavior of real gas approaches ideal gas. That means we have said that when the pressure, I gave you an example last week, right? Or 2 days ago. When the pressure is high, the molecules are closer to each other. When they are close to each other, the force of attraction and repulsion is very strong. And that is why you cannot use the pressure as an indicator of mechanical equilibrium. Right? So when the pressure is reduced to 0 or 1 atmosphere, the molecules are quite far apart. The force of attraction and repulsion are not strong, and it behaves like an ideal gas. Any real gas will behave like an ideal gas at low pressure. Okay? So at low pressure, viscosity of real gas is equal to pressure, right? We said that. Then for ideal gas also it is viscosity is equal to pressure. At low pressure, any real gas becomes like an ideal gas. So viscosity of real gas at low pressure is equal to pressure. At low pressure is equal to actual pressure. Okay? So gas at very low pressure, P0, is chosen as reference state, and we say that viscosity by pressure is equal to 1 at low pressure. F by P is equal to 1 when the gas, real gas, approaches ideal gas. Then only what will happen is pressure, viscosity will be equal to pressure. So then we define viscosity as limit when pressure tends to 0, viscosity upon pressure is equal to 1. That's what we are saying, right? At low pressure, viscosity is equal to pressure. Or F by P tends to 1 as P tends to 0. So at very low pressures, near about 1 atmosphere or so, the viscosity is equal to pressure, and that's how we actually define the standard state of viscosity. So standard state of real gas is a hypothetical state in which the gas is at a pressure P0 where it behaves ideally. So when you reduce the pressure of any real gas, if you take pressure gas at say 10 atmosphere or 100 atmosphere and reduce the pressure to 1 atmosphere, it will start behaving like an ideal gas. And that is the standard state for viscosity. समझ में आया क्या?
यस सर। और सर हाई प्रेशर होगा तो कैसे कैलकुलेट करेंगे viscosity?
नहीं, high pressure पे viscosity is not equal to pressure. That we'll see. We'll derive equation. We'll see what is the effect of pressure on viscosity. And then you'll see. Just like we did for chemical potential, we'll see what is the effect of pressure on viscosity. And then you'll see what is the effect. So at low pressure, viscosity is equal to pressure. But at high pressure, viscosity is not equal to pressure. And that is why we are defining all these things. Okay? Any doubts, questions? Before we proceed further. Clear है इतना? Is it clear or is there any doubt? You'll see some examples also, then you'll see realize when the pressure increases how the viscosity changes. There are some examples which you'll see. Just for the time being, remember that at low pressure, viscosity is equal to pressure when the gas behaves like an ideal gas, and at high pressure, viscosity is not equal to pressure, and we'll see how to get that viscosity for high pressure. Okay, so we define viscosity coefficient which is equal to F by P, which is equal to phi, right? And we have derived dg is equal, or defined viscosity as dg equal to RT ln F. So if we integrate between low pressure P0, P superscript 0 to P, what we will get is integral from F0 to F. What we get is G minus G0 is equal to RT ln F by F0. Since at low pressure, very low pressure, F0 is equal to P0 and F is equal to viscosity into P, right? We have defined F by P is equal to viscosity coefficient, right? So we can replace this G minus G0 is equal to RT ln F is equal to phi into P, and F0 is equal to P0. So what you'll get is RT ln P by P0 plus RT ln phi. Right? So you can take G0 on the other side and you get what you call Gibbs free energy for a real gas. This is for ideal gas actually, G0. So for a real gas, Gibbs free energy is equal to G0, which is for ideal gas, plus RT ln P by P0 plus RT ln phi. And we have seen for ideal gas, P is equal to RT ln P. So if we integrate similar to the previous one between P0 and P, what we'll get is integral from G0 to G, RT ln D, RT dln P, integral from P0 to P. So what we'll get is G minus G0 is equal to RT ln P by P0, which is for ideal gas. Right? So we can take this on the other side, and what we get is G for ideal gas is equal to G0 plus RT ln P by P0, which is this term. In this equation 6, G0 plus RT ln P by P0 is nothing but Gibbs free energy for ideal gas. Okay? Is this okay? Equation 6 and 7? Yes, no, don't know. Some
Yes,
answers
sir.
from.
Yes, sir.
Okay. So what we'll do is we'll substitute for this G0 plus RT ln P by P0 in this equation.
Sir, what is G in case of ideal gas? Pandit.
G in the case of ideal gas. We have seen this, no? Yeah, no? RT ln P. You have seen this. For ideal gas, G is equal to RT ln P plus C. This for real gas, ideal gas के लिए यहाँ पर P आ जाएगा pressure. Gives free energy. That's how we define, no? Starting from there only we read that. D is equal to RT ln P. क्या डाउट क्या था आपका? हेलो
सर G and G naught लिखा था ना इक्वेशन में, so G naught is for ideal gas.
हाँ, G is for real gas.
So ideal gas के इक्वेशन में भी G आया ना?
हाँ, तो ideal gas का था, ये real gas का है. You have written this for ideal gas, so this is G ideal. I can write probably superscript ideal gas यहाँ पर. वो नहीं लिखा मैंने, because here I have written ideal gas. I should write here G for ideal gas, DG for ideal gas is equal to RT dln P, and this is DG for real gas is equal to RT dln F. लिखा है ना यहाँ पर real gas के लिए. Only thing is मैंने यहाँ symbol नहीं डाला real gas. This is for real gas.
Yes, sir.
समझा क्या? That's exactly why we defined fugacity, because for real gas we cannot use pressure to calculate this Gibbs energy. So we have defined fugacity for real gas instead of pressure for ideal gas. Doubt clear हुआ कि नहीं हुआ आपका?
Yes, sir.
Okay, let's see, where are we? Okay. Right. So from this equation, you get G equal to G0 plus RT ln P by P0. This is for ideal gas. This we can write superscript ideal gas, right? यहाँ पर क्या है? G for real gas this for G for real gas is equal to, this is nothing but G for ideal gas plus RTLN phi. समझ में आया अभी? So G for real gas is equal to G for ideal gas plus RTLN phi from this equation. This was G for real gas. G0 plus RTLN P by P0 is G for ideal gas plus RTLN phi. ठीक है, अभी डाउट क्लियर हुआ आपका?
हाँ ये हो गया.
So essentially RTLN phi is the effect of intermolecular forces which is occurring in real gases. Ideal gas का तो पता है हमारे को क्या होता है. So we are basically accounting for intermolecular forces which we talked about in real gases by using this term RTLN phi. And all our gases behave as ideal gas as pressure approaches zero or low pressure, right? And we have seen fugacity tends to pressure as P approaches zero. Similarly, because fugacity coefficient is nothing but F by P, so if fugacity tends to pressure, fugacity coefficient will tend to 1 as P approaches zero. Right? So if fugacity coefficient is 1, that means it is an ideal gas. If fugacity coefficient is not 1, then it is non-ideal gas. ठीक है? Any doubts on this?
सर वो F2 by F1 is equal to P2 by P1 के बाद में जो आपने डेरिवेशन अभी दिखाया था ना, वो थोड़ा रिपीट कीजिए ना. हेलो 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 सर, मेरी आवाज आ रही है?
आ रहा है.
हेलो,
हाँ आ रहा है, आवाज आ रहा है, बोलो.
वो F2 by F1 is equal to P2 by P1 है ना, वो K is equal to आपने, हाँ उसके नीचे का जो अभी आपने बताया था ना, वो थोड़ा रिपीट कीजिए ना.
Okay. So यहाँ पर देखा था हमने, मेरी compared equation 3 and 4, right? Equation 3 is for real gases. Delta G for real gases is equal to RTLN F2 by F1. And delta G for ideal gases is RTLN P2 by P1, right? So when we say real gases includes ideal gases also, because at any real gas at low pressure becomes ideal gas. So for ideal gases, this equation 3 has to be equal to this equation 4, right? Delta G from this equation has to be equal to delta G from this equation. Okay? So in that case, right hand side has to be equal. What you get is RTLN F2 by F1 is equal to RTLN P2 by P1. RT cancel हो जाएगा. What you get is ln P2 by P1 is equal to ln F2 by F1. That means F2 by F1 has to be equal to P2 by P1. ठीक है? समझ में आया?
हाँ सर.
So when you say F2 by F1
Sir,
equal to P2 by P1, that means fugacity is directly proportional to pressure. You can write this as
सर वो समझे, उसके नीचे वाला जो अभी बताया था ना, अभी थोड़ी देर पहले आपने.
अरे क्या बताया था, एग्जैक्ट पिन पॉइंट करो ना.
अभी जो अभी आपने थोड़ी देर पहले रियल गैस वाला बताया था, तो
ये समझ में आया था.
हाँ ये समझ में,
ये समझ में आया.
इसके नीचे वाला इधर से चालू होता है वो.
इसके नीचे वाला, ओके, ये वाला. Okay, so we have dg equal to RTLN phi. So we integrate from low pressure P0 to P. So what we get is G minus G0 is RTLN F by F0. F0 is fugacity as low pressure and F is that fugacity as actual pressure. So at low pressure we have defined standard state fugacity is equal to pressure, right? So F0 is at low pressure, that is equal to pressure at low pressure. And we also defined fugacity coefficient as F by P. So F is equal to phi into P. तो अगर ये F से हमने डाला इक्वेशन में, what is RTLN F is equal to phi into P, F0 is equal to P0, right? So we can write this as RTLN P by P0. ये phi separate किया हमने, तो plus RTLN phi. This simple algebra. right? So we are saying कि G जो है, this is for real gas, is equal to G0, ये इधर लाया हमने right hand side में, plus RTln P by P0 plus RTln phi, right? So now if we take dG for ideal gas is equal to RT dln P. If we again integrate from P0 to P, what we'll get is G minus G0 is equal to RT ln P by P0. ठीक है, समझ में आया इक्वेशन 6 और 7?
सर आया अभी समझ में।
समझा कि इक्वेशन 6 और 7? So equation 7 say you can take G0 on the right side. What you get is G equal to G0 plus RT ln P by P0. Now this is for ideal gas, right? This is for ideal gas and this is for real gas, right? So we can write GR for real gas is equal to G0 plus P by P0 is G for ideal gas plus RT ln phi. ये लिखा है यहाँ पर. So G for real gas gives you energy for real gas is equal to gives you energy for ideal gas plus RT ln phi. And this term actually represents the intermolecular forces of a real gas. समझा क्या equation 9?
Oh yes sir, yes sir.
Okay, and we have defined by standard state F tends to P as P becomes zero or low pressure. So if you define this, then automatically phi is equal to F by P. So if F tends to P, phi will tend to 1 as pressure reduced to 0 or low pressure. ठीक है? Any doubts so far? Okay, so if it is clear, then let us proceed to next slide. Effect of temperature. इतना समझ में आया तो बोलो, नहीं समझ में आया तो बोलो. Any doubts on this equation 9? Okay, there is no comment. Let's proceed. So let's see what is effect of temperature on fugacity and effect of pressure. We'll see both. So now we define G0 molar free energy at very low pressure and F0 fugacity as very low pressure. That is for ideal gas, right? So G for real gas is equal to G0 plus RT ln F by F0. You derive किया हमने, right? This one, right? G is equal to G0 plus RT ln F by S0. ठीक है? So we can write same thing as R ln F by F0 is equal to T यहाँ पर लाया हमने G by T minus G0 by T. Similar to what we have done for chemical potential, right? Mu by T लिया था हमने वहाँ पर, right? लिया था कि नहीं, याद आ रहा है? Effect of temperature लिया था हमने chemical potential का. We had taken mu by T because that gives a simple equation. You can take mu also or G also, but the equation will not be very simple. So what you do is differentiate with respect to temperature at constant pressure. So what you get is R double ln F by double T at constant pressure minus, because ln F by F0 means ln F minus ln F0, so minus double ln F0 by double T at constant pressure is equal to double G by T by double T at constant pressure minus double G0 by T by double T at constant pressure. ठीक है, इक्वेशन 11 समझ में आया? Any doubts on equation 11? Okay, so then we'll use derive Gibbs-Helmholtz equation. H is equal to VdP minus SdT. We know that. So at constant pressure, we get double G by double T at constant pressure is equal to minus S, because this is equal to 0, dP is 0, so we get minus S. Now we take d of u by v, numerator and denominator, so that is equal to v denominator into derivative of numerator minus numerator and derivative of denominator by denominator square. So we take dou g by t at constant pressure is equal to denominator is t here into dou g by t at constant pressure minus numerator which is g and dou t by t is 1 divided by t square. ठीक है, इक्वेशन 30 समझ में आया? Just taking derivative of g by t with respect to temperature at constant pressure. So substituting 12 in 13, ये जो टर्म है ये यहाँ substitute करेंगे. So what we get is dou g by t at constant pressure is equal to minus, this is minus s यहाँ, so minus s into t minus g by t square. ठीक है, and we know g is equal to h minus ts, so minus h इसको इधर लाया तो is minus g minus st or ts, and this is what, this is a minus h, right, this term in equation 14. We can write minus h by t square. So what we get is dou g by t at constant pressure is equal to minus h by t square. This is Gibbs-Helmholtz equation. This is similar to what we saw in chemical potential, right? यहाँ पर क्या था इक्वेशन, याद है किसी को? यहाँ पर था dou mu I by t by dou t is equal to minus h I bar by t square. Exactly same. यहाँ पर g की जगह पर mu I हो गया था, because we are replacing Gibbs free energy with partial molar Gibbs free energy. H will be नहीं फर्क है, बाकी इक्वेशन सेम है, ये इक्वेशन आया था बिल्कुल. So if you remember you get similar equations. सिर्फ terms थोड़ा change होगा, because you're just replacing this Gibbs energy with partial molar Gibbs energy, so you have to replace this enthalpy with partial molar enthalpy. बाकी equations same है. This is called Gibbs-Helmholtz equation. And sometimes they ask you in exam for derivation of Gibbs-Helmholtz equation. Okay, so थोड़ा और बाकी है. You can finish it off in 2 minutes. So you can take equation 16 and substitute in 11. Okay, equation 11 ये था हमारा जो derive किया था हमने, पहले किया था. Now you take this thing and put in equation 11. So what we get is r into dou ln f by dou t at constant pressure minus dou ln f0 by t dou t at constant pressure, the right hand side, is equal to इसको minus h by t square में डाला ये इक्वेशन, और यहाँ पर माइनस h0, यहाँ पर g0 है तो h0 आएगा सुपरस्क्रिप्ट, right? So for ideal gases at very low pressure f0 is equal to p0. So equation 11 becomes, or this equation will become, because f0 is equal to p0, right? यहाँ पर p0 आएगा, so what we get is r ln d dou ln f by dou t at constant pressure is equal to h0 हो जाएगा plus minus h upon t square, and this term will become 0 at low pressure because there is no effect of temperature. Yeah, because this is essentially independent of temperature, pressure. P0 double then F P0 by double T is independent of temperature here, and that's why it becomes 0. So what we get is equation 17, which is showing the effect of temperature on fugacity. So if you can measure the enthalpy, we can find out the fugacity. Any questions on equation 17? Tomorrow we'll see the effect of pressure on fugacity. अभी है छोटा सा ही, but we'll see tomorrow. Okay. Any questions on this effect of temperature on fugacity? No comments, no difficulties. Okay, so think about it. I think I've added this on the Microsoft Teams files folder. You can check it out. And if you have difficulty, then you can ask tomorrow. Okay?
Okay, sir.
So I'll stop the recording.